Hello, mathematicians. We continue our study of quantified statements. And honestly, I was a little hesitant to even create this video because I can't say that there's a lot of new information and certainly nothing earth shattering here. Really, a lot of wrapping up of what we've talked about with quantified statements and really just an overview of what we've discussed. Now, this is perhaps a new vocabulary word, the rule of universal instantiation. It simply says if a property is true for everything in a set, then it is true of any particular thing in the set. So, suppose we say that all men are mortal and Socrates is a man. Therefore, according to the universal instantiation, Socrates is mortal. So, since it's true that all men are mortal and Socrates happens to be a specific example of a man, then Socrates is mortal. Again, I don't think that that's earth shaking news. This is a mathematical example of applying the rule for multiplying um, like bases where you add the exponent. So, if we wanted to multiply r to the k plus 1 times r, we would use the general rule. The general rule being this right here. We could apply it to this specific case to find that r is equal to, or r to the k plus 1 times r is equal to r to the k plus 2. Universal modus ponens. So we talked about earlier that modus ponens is when you have an if-then statement. You know that the if part is true, and so you conclude that the then part is true. Okay? So if A makes P of X true, and P of X implies Q of X, then A also makes Q of X true. Again, I don't think that that's a great earth-shaking revelation. So, for example, if an integer is even, then its square is even. K is a particular integer that is even. Therefore, we can conclude that K squared is even. Here's another example. For every x, if E of x, then S of x. E of k is true for a particular k. Therefore, we can assume that S of k is also true. Okay, suppose we look at this example. If T is any right triangle with hypotenuse C and legs A and B, then C squared is equal to A squared plus B squared. You'll recognize the good old Pythagorean theorem. The triangle shown at the right is a right triangle with both legs equal to 1 and hypotenuse C. Therefore, we can take this universal idea and apply it to this specific example, and we can say that C squared is equal to 1 squared plus 1 squared. Okay, this is an example of universal modus ponens in a proof, proving that the sum of two even integers is also an even integer. So if you kind of look down here, we've assigned 2r and 2s to represent integers m and n. When we add them, we get 2 times some integer. Therefore, we can say that m plus n is even. So if n is if an integer is even, then it equals twice some integer. M is a particular even integer, so we can say that m is twice some integer. Okay? If an integer is even, it equals twice some integer. N is a particular integer. N equals twice some integer. So then we can combine those together and say that if we add two evens, we get an even number. Modus tollens, you might recall, is the use of the contrapositive. Okay? So if P then Q is true, then not Q means not P is true. Just a reminder of modus tollens. So if A does not make Q true, then A does not make P of X true. All human beings are mortal. Zeus is not mortal. So you can think of this as if you are human, then you are mortal. Zeus is not mortal. Therefore, by modus tollens, Zeus is not human. All professors are absent minded. So, for example, if you are a professor, then you are absent minded. Tom Hutchins is not absent minded. Therefore, Tom Hutchins is not a professor by modus tollens. It is the contrapositive. Okay, this, I believe, is a definition that we have previously stated. So, just a reminder, to say that an argument form is valid means that no matter what predicates are substituted for the predicate symbols in its premises, if the resulting premise statements are all true, then the conclusion is also true. An argument is valid if and only if its form is valid. It is called sound if and only if its form is valid and its premises are true. Okay, we're going to talk a little bit about diagrams, in particular Venn diagrams, to test for validity. So consider the statement, all integers are rational numbers. We can see that according to the display, the figure, since all integers are rational numbers, we can display the set of integers as a circle inside of a circle, where the outer circle is the set of all rational numbers. Let's look at the statement, all human beings are mortal. Zeus is not mortal, therefore Zeus is not a human being. So we have this set of all mortals. Human beings are mortals. The major premise is pictured on the left. By placing a disk labeled human beings inside a disk labeled mortals. The minor premise is pictured on the right. Zeus is not a mortal. Therefore, Zeus is not in the circle of mortals. So clearly, he cannot be in the circle of human beings. So, this is a nice pictorial way of representing the fact that Zeus could not possibly be a human being if he is not mortal. All human beings are mortal. Felix is mortal. Therefore, Felix is a human being. So here we have the major and minor premises. All is known is that Felix's dot is located somewhere inside the mortal's disk. However, that does not necessarily mean he is inside the disk of the human beings. Perhaps he is inside the mortal's circle, but not inside the human being's circle. Therefore, this argument does not work. It is invalid. Again, perhaps Felix is a human being, but maybe not. Since we cannot assertively say that he is a human being, then our logic is faulty. The argument is invalid. So here we have using diagrams to test for validity. The converse error is very common. Again, if P, then Q. Q being true does not necessarily mean that P is true. So this causes an invalid conclusion. The inverse error is also problematic. If P, then Q does not mean that not P implies not Q. So that would be faulty logic. That would be an invalid conclusion. So let's look at this example. It says no polynomial functions have horizontal asymptotes. In other words, if the function is a polynomial, then it has no asymptotes. The function has a horizontal asymptote. Does that mean this function is not a polynomial function? Again, so no polynomial functions have asymptotes. So notice the diagram here. Functions with horizontal asymptotes and polynomial functions are disjoint circles. They are mutually exclusive. There is no overlap. Okay? The diagram shows this function must lie outside the polynomial function's disk. And so the truth of the conclusion necessary follows. So the argument is valid here. This is talking about transitivity. If P implies Q and Q implies R, then P implies R. So just a transfer of modus ponens and modus tollens. Skipping through the Tarski example. So a little remark. It says that one reason why so many people make converse and inverse errors is that the forms of the resulting arguments would be valid if the major premise were a biconditional rather than a simple conditional. Here's an example. It says all town criminals frequent the den of iniquity bar. John frequents the den of iniquity bar. Therefore, John is one of the town criminals. The conclusion of this argument is invalid. It results from making the converse error. Therefore, it may be false, even when the premises of the argument are true. This type of argument attempts unfairly to establish guilt by association. The closer, however, the major premise comes to being a biconditional, the more likely the conclusion is to be true. If hardly anyone but criminals frequent the bar, and John also frequents the bar, then it is likely, though not certain, that John is a criminal. On the basis of the given premises, it might be sensible to suspect John, to be suspicious of John, but it would be wrong to convict him. A variation of the converse error is a very useful reasoning tool provided that it is used with caution. It's a type of reasoning that is used by doctors to make medical diagnoses and by auto mechanics to repair cars. It's the type of reasoning used to generate explanations for phenomena. It goes like this. If the statement of the form for every x, if P of x, then Q of x is true, if Q of A is true for a particular A, then check out the statement P of A. It just might be true. For instance, suppose a doctor knows that for every X, if X has pneumonia, then X has a fever and chills, coughs deeply, and feels exceptionally tired and miserable. And suppose the doctor also knows that John has a fever and chills, coughs deeply, and feels exceptionally tired and miserable. On the basis of these data, the doctor concludes that a diagnosis of pneumonia is a strong possibility, though not a certainty. The doctor will probably attempt to gain further support for this diagnosis through laboratory testing that is specifically designed to detect pneumonia. Note that the closer a set of symptoms comes to being a necessary and sufficient condition for an illness, the more certain the doctor can be of his or her diagnosis.